So we're very happy to have Gary Horowitz from Santa Barbara, and he'll be speaking to us about a new type of extremal black hole, please.
Okay, thank you. It's a pleasure to be here, be able to speak at this meeting. I'd like to tell you about some work I did last fall with Oscar Diaz and George Santos, which is described in more detail in these two papers. But before I start, I should warn you, I'm a physicist, not a mathematician, so there'll be no proofs in this talk. All the results I'll describe are based on numerical calculations and approximations. Hopefully some of you will be able to prove these results rigorously. Okay, I'm going to consider standard four-dimensional asymptotically flat black holes. Nothing exotic like higher dimensions or asymptotically anti-de Sitter or anything else physicists sometimes consider. This is standard four-dimensional black holes. As you know, in Einstein-Maxwell theory, there's a maximum charge that can be carried by a black hole of given mass. And these extremal black holes are characterized by having a degenerate horizon with zero surface gravity. Now, there are standard sort of no-hair theorems, which show that when you add simple matter to the Einstein-Maxwell theory, nothing changes. As we just heard, these matter fields tend to decay, they radiate off to infinity or go down the horizon, and you end up with the standard Einstein-Maxwell black hole with the same type of extremal limit. However, for more complicated matter, there are changes to the extremal black hole. In particular, some theories of supergravity and string theory have scalars with exponential coupling to the Maxwell field. And in this case, the horizon often becomes singular in the extremal limit. That's just because the Maxwell field acts now as a source for the scalar. And in the extremal limit, the horizon moves infinitely far away in a space-like direction. And that the source now of the scalar field drives the scalar to arbitrarily large values in radial evolution toward the horizon. I'm going to consider a new theory with a Maxwell field and a charge scalar that has a new kind of extremal limit. The black hole with maximal charge for a given mass is going to be non-singular and has a non-degenerate horizon. So the, so the talk will consist of two parts. I'm first going to describe this theory and explain this new type of extremal black hole. And in the second part, I'm going to look inside the horizon of these new black holes, and we're going to find more surprising features. Okay, so here's the model, the action for the theory I want to consider. It consists, first of all, of the standard Einstein-Maxwell theory. Then I'm going to add a charged scalar field. This is a standard action for a scalar field with mass m and charge q. These script d's are just the sort of gauge covariant derivative, the usual covariant derivative minus iq times the vector potential for the Maxwell field, where f is just dA. The scalar field psi starts off as being a complex scalar field. And this is the new term. So I'm going to add one term to this standard theory. It's a sort of interaction between the Maxwell field and the charge scalar. And I'm going to give it a coefficient alpha. I'm going to choose alpha to be positive. And in that case, this theory satisfies all the usual positive energy conditions. All I'm doing is basically changing the coefficient of the Maxwell field by a positive quantity. So it will satisfy the dominant energy condition, all the usual energy conditions. And so this theory has a positive mass theorem. But this new term has an important consequence. It will make the standard Reisner-Nordstrom solution unstable. When you increase the charge toward extremality, Reisner-Nordstrom becomes unstable to turning on a static scalar field outside. You basically generate scalar hair. And you can see that from the form of the equations. So here we have, well, this is the Einstein equation. This is the Maxwell equation. And the last is the scalar equation. And what I want you to notice is that in addition to the standard mass term, the term we add gives sort of basically another effective potential for psi. For an electrically charged black hole, F squared is negative. And near the horizon, this negative sort of potential can overwhelm a standard positive mass term and make basically destabilize the scalar field and cause it to become non-zero. So we're going to study static, spherical, asymptotically flat charged black holes using a standard ansatz. So the metric will be spherically symmetric. There'll be two metric functions, which I'm calling P and G, both functions only of R. The vector potential will have only a time component, and I'll call that phi of R. And the scalar field, it turns out one can take it to be real. That's sort of a gauge choice. And I'll take it to be real and just write that as psi of R. Okay, one standard solution is the well-known Reisner-Nordström solution, where psi is just 0. P takes this familiar form in terms of these two constants, R plus and R minus, the inner and outer, or the radius for the inner and outer horizons. The other metric function is just 1. And the electrostatic potential can be written in this form. I'm choosing a gauge in which the potential vanishes at the horizon and is non-zero at infinity. The charge is mu times R plus. Mu is, of course, not an independent parameter. For Reisner-Nordström, mu squared is just the ratio of R minus over R plus. And so mu equals 1 in the extremal limit. Okay, now in order for this theory to have scalar hair, in order for the scalar field to be bound to the black hole, a certain asymptotic condition has to be satisfied. And that is that the charge and mass of the scalar field must be related to this asymptotic value of the electrostatic potential, mu, in this way. Q squared mu squared must be less than or equal to m squared. If Q squared mu squared is strictly less than m squared, a static scalar behaves asymptotically, as shown here. It falls off exponentially, as you might expect for a bound state. And you have two constants, b and eta. If this if Q squared mu squared is equal to m squared, the asymptotic behavior is a little more complicated, but it still falls off exponentially, like e to the minus the square root of r. But note that this is only possible if the charge and mass of the black hole satisfies this condition that q minus mu m is positive. I'm going to check. I think whoops. Yeah, I forgot to mention black holes in this theory depend on 5 parameters. There are 3 parameters in the Lagrangian: the mass and charge of the scalar and this new coupling alpha, and then there's the usual mass and charge of the black hole. But there's an overall scaling symmetry. So you can describe the solutions in terms of 4 dimensionless parameters, which I'll take to be the charge to mass ratio of the scalar, this new coupling alpha, and then some dimensionless mass and charge of the black hole. In the gauge where the vector potential vanishes at the horizon, we're going to call mu the asymptotic value of this vector potential, and we can use mu instead of q, the charge of the black hole. And so that will be an important parameter, and that's what appears in this asymptotic condition. Okay, so the first step is to see when Reisner-Nordström becomes unstable in this theory. And so we look for look at non-extreme black holes, Reisner-Nordström with q less than m, and you can detect the onset of the instability by looking for a static finite energy linearized solution for psi. And we've checked that these actually mark the transition between stable and unstable quasi-normal modes. So if you take your scalar field, now time-dependent, expand, this usual harmonics, so it's give it an e to the minus I omega t time dependence. You look for solutions which are ingoing at the horizon, outgoing at infinity. They exist for only a certain discrete set of complex frequencies. And what I'm showing here is a plot as a function of the charge on the black hole, which I'm denoting by mu. So we fix the mass, increase the charge, so mu increases to the right. The blue curve is the real part of the lowest quasi-normal frequency. The green curve is the imaginary part. The red dot was the zero mode, this static finite energy solution. And indeed, the quasi-normal modes go from being damped to exponentially growing right at this point. So that is the onset of the instability. And then we just numerically construct the full nonlinear solutions describing black holes in this theory for various parameters. And you get a plot that looks like this. So I'm taking the parameters to be alpha equal to 1. That's the new coupling. And the charge to mass ratio of the scalar field to be 1. The plot has the charge minus the mass, the difference between the charge and mass of the black hole on the vertical axis versus the mass of the black hole. So the black holes are getting bigger when you move to the right. So when Q is equal to M, that's 0 on this vertical axis. These are the usual extremal Reisner-Nordstrom black holes. And this green shaded region below that are the usual Reisner-Nordstrom black holes. Okay, so we have all the usual Reisner-Nordstrom black holes in green. The blue curve is the onset curve for this instability. And above the blue curve, this brown shaded region, are all of these new hairy black holes with charged scalar hair outside the horizon. These black holes exist. You can keep increasing the charge for a while. If the black hole is small, so that M is small, these end on singular solutions. So these are not much different than what we had seen before in string theory, that there are these hairy black holes with singular extremal limits. But if M is bigger, these hairy black holes end on this red curve, which is the curve when mu is 1. That's the curve which saturates this asymptotic condition that we needed for the scalar field to be bound to the black hole. And so that's what we're going to, well, let me first point out the hairy black holes have Q bigger than M. They're exceeding the usual extremal bound. That's not really surprising since the scalar field carries charge. So you can have charge, the total charge in the spacetime includes the charge on the black hole and the charge on the scalar field outside. But it turns out that even if the scalar field was neutral, if you set Q to 0, hairy black holes can have Q bigger than M. Since the conserved charge in this theory, because of that extra term, the charge which is conserved is not just the integral of the dual of F as usual, but it includes this extra factor. So the charge on the black hole can be, say, Q equal to M, but the total charge, the charge that's conserved at infinity, can be bigger. Okay, if you now look at properties of these mu equal to 1 black holes, which have the maximum charge per given mass for these hairy black holes, what I plot here is the area of the black hole. I called it S because it's related to the black hole entropy, but this is basically just the area of the black hole. This is the surface gravity of the black hole. You see the surface gravity is not 0. I called it T because it's related to the temperature, Hawking temperature of the black hole. But this is just showing that these are non-degenerate black holes, non-zero surface gravity, non-zero area. They have maximum charge for a given mass, but are non-singular with non-zero surface gravity. So these are the new extremal black holes I was referring to in the title. These plots on the bottom show you the electric field on the horizon as a function of mass. I should say all of these are functions of mass on the horizontal axis, and they end just when the red curve ends, when these mu equals 1 black holes become singular. This is the electric field on the horizon as a function of mass, and this is charge on the black hole in the bottom right as a function of mass. You notice the charge on the black hole basically decreases linearly with the mass of the black hole, but since the area is also decreasing almost linearly, the electric field on the horizon stays approximately constant for a while until it gets very close to the singular endpoint, and then the electric field rapidly diverges, and that boosts the instability, and the charge on the black hole quickly goes to 0. Okay, so these new kind of extremal black holes exist due to a trade-off. As you increase the charge, the region near the horizon wants to become singular. You have this potential for the scalar field, which is driving it to large values. But before one can reach the singular horizon, the asymptotic condition can be saturated. And then you have, well, you can't support scalar hair if this asymptotic condition is violated, and there are no other black holes without hair having Q bigger than M, and therefore the maximal charge black hole has a smooth, non-degenerate horizon. Okay, let me say next what happens if you vary the parameters. So I'm first going to vary this coupling alpha, and I'm still going to keep the charge to mass ratio of the scalar field equal to 1. So these are different curves. The red curve is the one I showed you before with alpha equal to 1. And then there are curves for alpha equal to 5, 10, and 100. And these are simply the maximal charge for the black holes. So you should picture that below these curves are this region is all filled in with hairy black holes. There are static spherically symmetric solutions with scalar hair outside the horizon. The edge here, the other boundary, is a singular solution. So I haven't drawn that explicitly, but there is some boundary like you saw in the black curve before, going from this endpoint all the way down to the origin over here. So this is again Q minus M of the black hole versus M. And you see basically two main effects. You see that increasing alpha increases the charge that these black holes can carry. This scale is much bigger than it was when alpha's 1 is way down here. And that's simply because you increase the instability. This term driving the instability has gotten a lot stronger. You can put more scalar field outside the black hole, increasing the charge. But you also notice that the onset, these non-singular extremal black holes now only start to exist at a larger value of the mass. So that's because the increasing the strength of this new term increases the potential driving the scalar to large values, and it can become singular before you reach this, before you saturate the asymptotic condition. Okay, that's what happens when you increase alpha. What happens when you change the charge to mass ratio of the scalar? So we're going to go back and set alpha equal to 1. And it turns out that these new black holes are very sensitive to changing this charge to mass ratio. If you increase it above 1, the maximum value of this electrostatic potential at infinity is now less than 1. So these hairy black holes only exist if the black hole is small enough. We've reduced the maximum mu, so that means we've reduced the maximum electric field on the horizon, but you need a large enough E to trigger the instability, and that's only possible for small black holes. It also turns out that the new extremal black holes now can exist to arbitrarily small masses. So we don't have a minimum mass where they become singular. as soon as Q over M is bigger than 1.1. And that's just because we've reduced this maximum mu, and so you reach it sooner, and you can reach it before the horizon becomes singular. So next, if we decrease the charge to mass ratio, this maximum mu becomes larger. So that makes it harder to form the black holes before the horizon becomes singular. So that increases the minimum mass for these solutions to exist. But there's also a maximum mass, because we said that if this asymptotic condition is saturated, you have solutions only when the black hole charge is bigger than mu times the black hole mass. Now, it's not a problem when the maximum mu is less than 1, because whenever Q is bigger than M, it'll be satisfied. But now, if Q over M is less than 1, you get a maximum mu which is bigger than 1. And now this condition can be violated for large M. So these new extremal black holes, which are non-singular, only exist for a finite range of masses. And in fact, it rapidly shrinks. And as soon as Q over M is less than 0.99, you decrease it by 1%, these solutions stop existing, and the upper bound, the extremal limit, is singular for all masses. Okay, so all of these properties are shown in this plot, where I plot the charge minus the mass of the black hole on the vertical axis versus the mass on the horizontal as before. This is, the red curve is the Q over M equal to 1 curve, as we saw before. But now coming down here, we're increasing Q over M. So this is 1.05, 1.1, 1.15, 1.2, etc. And you see that these, the new extremal black holes, these are all curves which saturate this asymptotic bound. So now they only exist for small mass. The place where the minimum mass, as I said, quickly goes to 0. So as soon as it's Q over M is bigger than 1.1, there's no singular extremal limit. These are all non-singular extremal black holes with non-degenerate horizons. But you notice the maximum charge these black holes can carry is also shrinking. And as soon as you get down to, charge to mass ratio of 1.3 or so, the maximum charge the hairy black hole can carry is less than the maximum charge of Reisner-Nordström. So once you get to those parameters, the maximum charge and the maximal black hole, extremal black hole, is going to be the usual extremal Reisner-Nordström. Going the other way, if you decrease Q over M, as I said, you now have a minimum mass and a maximum mass. This blue curve here is when Q over M is 0.994. And as soon as you get down to 0.99, it just completely shrinks. The upper limit is a singular curve going out this way, another singular curve coming down. And if you decrease Q over M more, you just get the upper bound being a totally singular boundary. Okay, let me say just a word about, let's see. Some open questions. So one is, what characterizes the class of theories with these new extremal black holes? I gave one example. I added this psi squared, f squared to the action, but one can ask what class of theories will have them. You can ask if they exist in more than 4 dimensions. I don't see why not. And finally, how does the addition of rotation affect them? It's known that Kerr black holes can develop massive scalar hair near extremality, even without adding any extra interactions. That was shown back in 2014. So you can ask, can just the Kerr couple to a massive scalar? If you look at the extremal limit of that black hole, might it have a non-zero surface gravity and a non-degenerate horizon? I don't think that's known yet. Okay, let me now turn to the question of what happens inside the horizon of these black holes. Just after the onset of scalar hair, so I'm now going to focus on just this sort of threshold, the instability when the Reisner-Nordstrom black hole first becomes unstable and increasing Q just above it. Outside the horizon, these black holes are totally boring. The scalar field is very small everywhere, and basically it doesn't do anything. But we'll see it has a big effect inside the horizon. And in this regime, the dynamics inside the horizon sort of falls into three distinct epochs. And we call the first epoch collapse of the Einstein-Rosen bridge. And then we have an epoch which we call Josephson oscillations of the scalar field. And finally, we enter an epoch which we call the Kasner epoch, and there can be possible transitions to new Kasner epochs. One can show that there's no Cauchy horizon. Once the scalar hair turns on, the horizon, the inner horizon is destroyed and replaced by a space-like singularity, essentially a Kasner singularity. But the remarkable thing is that which Kasner singularity, I'll review this in a little while, but there is a one-parameter family of Kasner solutions, and which Kasner singularity you approach turns out to be extremely sensitive to the black hole parameters near the onset of this instability. Now, I should mention that Van de Mortel recently wrote a very nice paper proving analogs of these, the first and third epoch for the case of a neutral scalar field. So he starts with a constant neutral scalar field, small, on a Reisner-Nordstrom horizon, and proves studies the dynamics inside, and actually finds analogs of these, the first and third epoch. I believe he will talk about this on Thursday. Okay, so we're going to adopt a slightly different ansatz for the interior solution. The vector potential and charge scalar will be very similar. We're simply adopting a new radial coordinate z rather than r. The metric for the ansatz the ansatz for the metric is different. The metric will still be spherically symmetric, but I'm choosing it to write it in this way with the parameter kappa. The case of interest is kappa equal to 1, so this is a round sphere, but keeping kappa lets us identify terms in the equations depending on the curvature of the sphere more easily. Our two metric functions are now f and chi, as opposed to p and g before. They're functions of just this one radial coordinate z, and z is just related to our old r by r plus over r. So, and we're going to require that f vanishes at z equal to 1. So that means the event horizon will be fixed at z equal to 1. And as we evolve inside, we increase z, and z equal infinity is the final singularity. So using dimensionless variables, we just take q tilde to be the charge to mass ratio, y tilde to be r plus times m. We get a bunch of the field equations. They're just a bunch of ODEs that are complicated and messy. And so we have to study them. And the way we're going to study them, sorry, I have to, okay, well, let me first show you why there's no inner horizon for this solutions once you have a scalar field turned on. Okay, so the equations I just showed you imply that you have a certain constant of motion. There's a constant of this radial evolution, which takes the following form. So there's a term involving f, a term involving this electrostatic potential phi, and then an integral from the horizon to this whatever z you want of this metric function chi. Okay, so this turns out to be independent of z. Now at a horizon, F, of course, vanishes. That's the characteristic feature of a horizon. And you notice the equations of motion have lots of terms with 1 over F in it. But these terms always appear with the product of the scalar and the electrostatic potential. So if we're going to look for solutions with non-singular horizons, either psi or this capital phi has to vanish at the horizon. But you can show that if the scalar vanishes at a horizon, then all derivatives of it off the horizon must also vanish. So if we assume analyticity or something like that, it would say the scalar field has to vanish identically, and we don't want that. We want to assume we have a non-zero scalar field, so we're going to require that the electrostatic potential phi vanish at the horizon. Well, if we then calculate this constant at the event horizon, phi is 0, so this term doesn't contribute. This integral is trivial. We don't integrate anything, so that's 0. And we get just the first term, and it's given by this expression in terms of the derivative of f. But f is positive outside the event horizon and negative inside the event horizon. So its derivative must be negative. So we conclude that at the event horizon, C1 must be negative. If there was a smooth inner horizon, f would be negative between the inner and outer horizon. Sorry, f would be negative between the inner and outer horizon, becoming positive when you pass the inner horizon. So its derivative would be positive. If we evaluate the constant there, we get now a positive first term from the derivative of f. Third term, the second term doesn't contribute since phi is still 0. The third term contributes, but that's just some positive integral. So we conclude that this constant has to be positive. But it's constant. It can't be negative on one horizon and positive on the other. So that is an argument, at least, that you cannot have a smooth inner horizon once the scalar field turns on. Okay, so our strategy, we have these complicated ODEs. And our strategy is that we're going to start with data on the event horizon that we get from solving the exterior. And we just numerically evolve to large Z. And we see from the numerics that there are these different epochs, different types of evolution. And so to understand them better, we simply drop certain terms of the equations of motion that are negligible in the region of interest. This is just looking at the numerics. We say, okay, these terms are small. They're not seem to be playing a role. We drop them. We can then identify terms which seem to be the most important and solve those analytically. So we get analytic approximations for these regimes, and then we go back at the end and compare the full numerical evolution with the solutions for these approximate solutions. Okay, so the first epoch is the collapse of the Einstein-Rosen bridge. Again, we're starting with Q just slightly bigger than this critical charge, which is the onset of the instability. Psi is very small at the horizon. And in fact, it will stay small inside the horizon until you approach the former Cauchy horizon. Then it changes rapidly, causing a very rapid drop in GTT. And so by looking at the field equations and dropping the unimportant ones, you can derive an isolated or decoupled equation for this metric component GTT. It approximately satisfies the second order ODE for a small constant C1, which is directly proportional to the value of the scalar field on the event horizon. The solution of this ODE is given here in terms of two constants of integration, C2 and Z0. So now if Z0 is going to be some value which is close to the former Cauchy horizon. So if Z is less than Z0, the right-hand side is positive, and the solution is dominated by this second term here. And so GTT just is going to 0 linearly, like Z0 minus Z. However, once Z gets bigger than Z0, this becomes negative, and so the solution is dominated by the first term. And so GTT now goes to 0 exponentially in z minus z naught with a very large coefficient, because remember C1 is extremely small. And so what it shows you is that as soon as, it's very nonlinear dynamics, as soon as the scalar field turns on and is non-zero at the horizon, you get an e to the minus 1 over that small epsilon squared type of decay at this point. We call it a collapse of the Einstein-Rosen bridge just because in the usual picture, the Einstein-Rosen bridge going through the interior of the black hole is, well, you can take two different values of t, a large value of t, a small value of t, look at the distance along a constant r surface. Of course, t is a space-like coordinate, and that distance shrinks extremely rapidly because of this behavior of GTT. Okay, so here's a check of that approximation. I'm plotting GTT in a log scale. So this is a log scale on the vertical axis versus z. The full numerical solution is given by the solid curve. The analytic approximation is given by the dashed curve. And you see it agrees very well for some region here, showing this very rapid decay of GTT. Notice the values of z are close to 1. This still corresponds to the former Cauchy horizon because the onset of the instability is very close to the former extremal limit of the black hole. Okay, let me say a word about the next epoch. That's after the collapse of the Einstein-Rosen bridge, one finds that the scalar field essentially satisfies Bessel's equation. So you can write the solution in terms of the two independent solutions of Bessel's equation with coefficients C4 and C5. The argument of Bessel's equation involves a constant C3, which is very large. This constant C3 is proportional to 1 over C1 squared. So it's proportional to 1 over the value of the scalar field at the horizon squared. This is called Josephson oscillations just because in this regime, the electrostatic potential is essentially constant. And so that's what we're calling phi naught. And t is a space-like coordinate. So the non-zero component points in a space-like direction. That can be viewed as some sort of phase winding of psi. And in the theory of superconductors, that leads to oscillations, which are these Josephson oscillations. So here's a picture of those Josephson oscillations, now setting in at slightly larger values of z. And once again, there are two curves. The solid curve is the actual full numerical solution, and the dash curve is just those solutions of Bessel's equation. So it's a good approximation. Okay, finally, we come to the Kasner epoch. At the end of the Josephson oscillations, psi grows logarithmically in z. So we can write it as some constant beta times log z. And you find that all the other metric components are a simple power of z. And solutions of this kind, well, this is what we call the Kasner epoch, because there is a famous solution of Einstein's equation, the Kasner metric, which is a homogeneous anisotropic vacuum solution of general relativity, usually written in the form here. So tau is a proper time, and all the metric components are just powers of tau. The three exponents, px, py, and pz, have to satisfy two conditions for the metric to be Ricci flat. They have to sum to 1, and the sum of the squares has to be 1. You have three exponents, two conditions, so there's a one-parameter family of Kasner solutions, and these are the vacuum ones. Of course, we don't have vacuum GR. We have a scalar field and a Maxwell field. So when the Maxwell field and the curvature on the sphere are both negligible, there's a Kasner-like solution to our equations with the scalar field included. And converting z to proper time, you can write that in the following way. So now I'm using the fact that we have symmetry on the sphere to say that the exponent on this sort of x and phi directions has to be the same. So we get only one less exponent in the metric, but we have a scalar field with some coefficient of this logarithmic growth. So we get another exponent or another coefficient from the scalar. So again, there's three unknowns. If they satisfy these two conditions, then our field equations with scalar field are satisfied. So these are just scalar field generalizations of the Kasner solution. We have a one-parameter family of solutions, and it's convenient to parameterize that with this parameter beta, which we see in our solution as simply the coefficient of the logarithmic growth of the scalar. In terms of beta, the exponents you see here, pt, px, and psi, can be given explicitly by these expressions. And these expressions satisfy the two conditions. Okay, so what about the Maxwell field? Well, in this regime, the Maxwell field behaves as follows. If there's some constant, psi k, and then a function of z, which takes the following form. Ek is also a constant here. And so you see that if beta squared is bigger than a half, and if this Maxwell potential is small initially, as you evolve further in z, as z goes to infinity, this is just going to become more and more negligible. So if beta squared is bigger than a half, which means that GTT is initially decreasing in this region, the Maxwell field just remains negligible. And now you can compute beta by matching onto this Josephson oscillations. And you find that it's an oscillating function of the black hole parameters. In fact, we get a approximate form where beta is given by constant times sine of something constant over q divided by q critical minus 1 plus a constant. So that looks like this. This is a plot of that parameter beta, which is telling us which Kasner epoch we're in, which Kasner solution we're approaching, as a function of the charge on the black hole. This is q divided by the critical charge for the onset of the instability. And you can see the tiny, tiny changes. This is changing the charge by 1 part in 10 to the 5. But this is just, rapid oscillations that you could see from the form of the beta I gave you a moment ago. Again, there's a solid curve with the full numerical solution, the dash curve with just that analytic approximation. And whenever beta squared is bigger than a half, so beta bigger than about 0.7 here, whoops, in all of these, for all of these cases, this is the final value of the singularity. The singularity approaches Kasner with that beta. But what you see is that this parameter governing the singularity oscillates through a finite range an infinite number of times as you approach this critical q. It's just incredibly sensitive. Now, what happens if beta squared is less than a half? Well, if it's less than a half, the Maxwell field starts to grow. And when it grows, it causes a transition from one Kasner regime to another. And so here is an example of some solutions where this is z times psi prime. So when it's constant, this is basically the coefficient of a log. If this is approximately constant, it is beta, the coefficient of a log z behavior. And that's as a function of z. And you see now we're up to very large values of z because this takes a long evolution in z to see these transitions. But here's a case where we start with 5 different curves with the initial beta all less than sort of 1 over the square root of 2. And at some point, they just undergo a transition to a different value of beta, which is larger than 1 over the square root of 2. So this is what we call a Kasner transition. And this can happen again because we have examples. This is now changing the charge by basically 1 part, I think, in 10 to the 10. You have solutions where the initial betas are all almost indistinguishable, but you go through a transition, and sometimes the final value of beta is positive, and sometimes the final value of beta is negative. So you clearly access all possible values. There'll be values where beta squared after the transition is again less than a half. That can evolve, and it can be repeated. And so after our work came out, Mark Henault recently put out a paper showing that this type of dynamics that we found numerically falls into a scheme that they call cosmological billiards. It's related to this old Bikhail, Belinsky, Kalatnikov, Lifshitz behavior approach to a cosmological singularity, which showed repeated epochs of different Kasner behavior. That had not been studied before for charged scalars and Maxwell fields. We're finding something similar in the inside these black holes, and Mark Henault confirmed that that is indeed similar to what was happening in the other story. Okay, let me conclude. We studied black holes in an Einstein-Maxwell charged scalar theory with a new f squared psi squared coupling. We saw that increasing Q at fixed mass causes the Reisner-Nordström solution to become unstable and develop scalar hair. The black hole with maximal charge can have a smooth, non-degenerate horizon. There is intricate dynamics inside the horizon, as we just saw, and the region near the singularity is extremely sensitive to the charge on the black hole near this onset of this scalar instability. And I will stop there and take any questions.
Thank you, Gary.
Thank you.
All right, questions? Yes, Maxime.
So thanks for the talk, and this is really a very beautiful set of work I find. So thanks for that. I wanted to ask, so this model that you look at, the phi square f square model, does it have, so first of all, how is it motivated physically, and second, does it have stationary solution even on Minkowski if you don't couple with a black hole? Does it have non-trivial stationary states?
Let's see, there are solutions. Yes, there are solitons in this theory that don't have black holes. They are not related to the black hole solution. So you can check the mass and charge of the solitons. You have to include gravity, right? These are self-gravitating. I don't know if you were asking for that or you wanted just a theory without gravity.
Even without gravity, I'm wondering, for example, comparing to these Young-Mills, because if you have Young-Mills, you can also have hairy black holes, and of course you have the Barney-McKinnon as well, right? So I was wondering if it was a little bit the same.
Well, what we looked at is we can take away the black hole horizon, and if we keep the coupling to the metric, to keep gravity, there are static non-singular solitonic solutions. Their charge to mass ratio don't overlap with the parameters we have for our hairy black hole. So they're not the result of shrinking the black hole to zero size or something like that. But if you're asking just about taking this theory in Minkowski space without gravity, I don't know. I don't think we looked at that. Yeah, I guess I'd be a little surprised if there are static solutions in that case, but we didn't really check that.
And can I ask also really quickly, do you usually when you have hairy black holes like that and you perturb them outside of static data, you expect instability, right? Do you also have instability here? What do you expect?
Oh no, we expect these are stable.
Stable to non-static perturbations.
Sure, yeah, stable to non-static perturbations, because these, yeah, and we expect that. I mean, we didn't do the time-dependent problem. But if you take an unstable, you take Reisner-Nordström in the unstable regime and put an arbitrarily small perturbation, we think they will evolve toward the static solutions that we've constructed.
In the exterior, that is. In the exterior, right?
In the exterior, for sure.
Right, okay.
In the interior, I don't know. Yeah.
Probably at least in spherical symmetry, but then maybe outside, I don't know yet, maybe.
Right, yeah.
Okay, thank you very much.
There is a hand raised in the attendees. Marios. I don't seem to have the ability to enable you to speak, Marius. We can't hear you, no, but we can see your chat comments. Oh, now you're allowed to talk. Yeah, okay, you should be good.
Okay, hello.
Hello?
Again, congratulations on the talk, very nice. Maybe I want to ask a few questions related to the ones that Maxime already asked about the perturbation of, of these kind of black holes, and what kind of, you said that you expect to be stable, right?
The exterior, I expect to be stable, yes.
Right. So if I take for example, like the extremal Rising-Nordstrom perturbations of such black holes, like we know that they're unstable, right, along the event horizon.
That's the Asymptotic instability.
Yeah. So
Yeah.
I'm trying to maybe compare like these what you're saying, the results to what you add, this scalar, the coupling term, and I have a feeling, my guess would be that you would have an unstable, again, at least along some like hypersurface, like if it's not the horizon, maybe there's an inner surface on the inside. But I would imagine that there's still like something similar would happen. You said on the exterior it's stable. Maybe on the inside something happens. I don't know. You have more data on that one?
Well, okay, I'm giving you my impression. We haven't studied, perturbations of this, but based on other examples we have of black holes that develop scalar hair, I certainly expect these are, first of all, the instability starts for the non-extreme case. So you were making an analogy with the extremal Rising-Nordstrom instability. So normally non-extreme Rising-Nordstrom is stable if you don't add this extra term, or that's, I guess, expected to be stable. And so with this extra term, the non-extreme Rising-Nordstrom becomes unstable near extremality, but still a finite distance away. And the endpoint of that instability under dynamical evolution, we expect to be these hairy black holes. And then if you perturb them with time-dependent perturbations, I expect that to stay. If you're away from the extremal limit, I should say, if you're away from these actual extremal hairy black holes, I expect them to be stable. The extremal hairy black holes might have instabilities where you can, I mean, basically you can try to destabilize the hair and have it to start to leak away or something.
I see. I would like, maybe would there would occur in some kind of, I have a feeling that from the equation, the wave equation you wrote in the first slides, they're very precise, like coefficients that contribute to this Asymptotic constants you're referring to. And I'm imagining that this instability would probably occur around R equals to a constant, a function of A, where A is the coefficient that you gave. That's my guess. Exactly. There's not anything rigorous here. I'm just trying to understand that from the extremal case without the coupled term. Anyway, thank you very much for your.
Yeah, I should make it clear that, I mean, our analysis of the interior, is based on these, basically taking the static hair and evolving in. So, we've assumed things are independent of T and they just depend on R, or, right, my Z coordinate. So if you have actual decays, time-dependent things outside the interior, the Cauchy horizon should still be unstable, or at least become singular, I fully expect, but it could be that these epochs we find are modified in some way.
Thank you.
All right, well, if there's no further questions, let's